For 10,000 years, bread was the food that kept us alive. Today, it is blamed for making us sick. Did human bodies suddenly revolt against wheat? Or did the wheat itself change? The story of a forgotten ancient grain with just 14 chromosomes found inside a 5,000-year-old mummy exposes what we lost and why it matters now. If we erase the wheat that once healed us, what did we unleash in its place? In 1991, high in the Ötztal Alps, hikers stumbled on a frozen body emerging from melting ice. Scientists would later call him Ötzi the Iceman, whose life ended over 5,000 years ago, but whose story was just beginning to be told. When researchers examined his stomach, they discovered the remains of a simple meal: ibex meat, wild plants, and most tellingly, tiny fragments of einkorn wheat. This was no wild grass. It was a domesticated crop shaped by human hands and careful selection. Radiocarbon dating anchored Ötzi's last days to 3,300 BCE, a time when agriculture was still a new experiment in the mountains of Europe. The presence of einkorn in his gut is a silent record. People were not just gathering what nature offered, they were growing and eating this ancient grain, passing seeds from one generation to the next. The story of einkorn stretches back even further to the hills of the Fertile Crescent, in what is now southeastern Turkey. Archaeobotanists have traced the first deliberate harvest to nearly 10,000 years ago, when small farming communities began planting einkorn alongside barley and emmer. These early farmers were not just surviving. They were building the foundation for settled life, for villages, for civilization itself. Ötzi's last meal becomes a time capsule, proving that einkorn was not a relic, but a staple woven into the fabric of daily existence. For thousands of years, this wheat sustained families from the river valleys of the Near East to the high passes of the Alps. It was the original staff of life long before modern grains and industrial fields changed the story. Strip away the centuries, and what remains is a grain with a genetic code as simple as it is ancient. Einkorn carries just 14 chromosomes, a diploid blueprint. Modern bread wheat, by comparison, is a genetic giant packing 42 chromosomes into each cell. That extra DNA is not just academic, it brings along the D-genome, a set of instructions that rewrites how wheat behaves in the body. Einkorn lacks this D-genome entirely. The gluten in einkorn is structurally different. Built from a more fragile network, it contains fewer of the stubborn immune-triggering peptides that make modern wheat so hard to digest for many people. Scientists have mapped the most problematic fragments like glia alpha 9 to the D genome, which simply does not exist in einkorn. While einkorn still contains gluten, its protein structure is less elastic, more easily broken down by enzymes, and less likely to provoke the same inflammatory response. Nutritionally, einkorn stands apart. Lab analyses show it routinely delivers about a quarter to a third more protein than standard red wheat, depending on the field and the year. Its golden color comes from a rich store of lutein and other carotenoids, 2 to 4 times higher than most modern varieties. Iron and zinc also appear in greater concentrations, especially when grown in low-input soils. In direct laboratory comparisons, ancient einkorn repeatedly wins on protein, minerals, and antioxidant pigments. This is not nostalgia. It is a measurable difference written in the DNA and confirmed in the flour. In the decades after World War II, a new breed of wheat began to sweep across the world's fields. The old towering stalks, some reaching nearly 5 feet, gave way to a new compact form, semi-dwarf wheat. This was not a minor tweak. It was the result of a deliberate campaign led by agronomists like Norman Borlaug and teams at international research centers in Mexico and India. Their aim was clear: end hunger by boosting yields? The answer came from a gene borrowed from Japanese Norin 10 wheat, shrinking the plant's height and thickening its stem. Suddenly, wheat could soak up heavy doses of synthetic fertilizer without toppling over, a problem called lodging that had haunted farmers for centuries. The results were dramatic. Fields that once yielded 1 ton per hectare now produce 2 or even 3. India and Pakistan, once on the brink of famine, saw harvests soar in the late 1960s and early 1970s. Governments and development banks pushed for rapid adoption. Seed catalogs phased out the old land races. Extension agents fanned out across continents, urging farmers to plow under their ancient hulled grains and plant the new miracle varieties. Within a generation, thousands of traditional wheat types vanished from commercial fields. Einkorn, already a minor crop, retreated to isolated valleys in Turkey and a handful of Italian hillsides, replaced by high-output, fertilizer-hungry hybrids. The semi-dwarf takeover was not just a story of new genetics. It was a global shift in farming priorities. Yield became the only metric that mattered. Diversity, resilience, and nutrition faded into the background. The world's wheat genome narrowed, optimized for industrial agriculture and global trade. By the 1980s, the old tall wheats were almost gone. What survived was a single engineered template, short, efficient, and utterly transformed. Celiac disease was once considered so rare that many doctors doubted its existence. By the turn of the 21st century, something had changed. Blood banks and hospital records began to reveal a pattern. The number of people with celiac-specific autoantibodies had climbed fourfold in just 50 years. In the 1950s, only about 1 in 500 Americans tested positive for these markers. Today, it is closer to 1 in 100. Similar trends appeared in Finland, the UK, and across North America, even after accounting for better diagnostic tools and growing awareness. This was not just a matter of more people getting checked. Something in the environment or in the food supply was provoking the immune system to attack the gut in ways it had not before. Researchers started searching for suspects. One theory pointed to a tiny fragment buried deep in the gluten protein, a chain of 33 amino acids called the 33-MER. This peptide, found in higher amounts in modern wheat, resists breakdown by human digestive enzymes. When it reaches the small intestine intact, it can trigger an immune response in genetically susceptible individuals. In laboratory studies, the 33-MER binds tightly to HLA-DQ2 and DQ8 molecules, setting off the cascade that leads to celiac disease. Modern bread wheat, with its extra D genome, produces more of these stubborn fragments than ancient varieties like einkorn. But the case is far from closed. Leading gastroenterologists warn that the rise in celiac disease likely has many causes, including changes in infant feeding, the gut microbiome, antibiotics, and even hygiene. Some studies suggest that total gluten intake has not increased as much as the prevalence of the disease. The 33-MER is a compelling suspect, but experts caution that correlation does not prove causation. For now, the evidence points to a complex interaction. Modern wheat's altered proteins may play a role, but they are only one piece of a much larger puzzle. Across the Canadian prairies and parts of the northern United States, a new harvest routine has taken hold. Farmers facing unpredictable weather and tight schedules often spray wheat fields with glyphosate just days before the combine rolls in. The chemical does more than kill weeds. It dries the crop, making harvest faster and more uniform. This practice, called pre-harvest desiccation, is especially common in wet years and in spring wheat, but it is not the global standard. In much of Europe, pre-harvest glyphosate is rare or outright banned. In the United States, it is used on a minority of acres, mostly in the north. Food safety agencies in Canada and the United States routinely detect glyphosate residues in wheat and flour, though almost all samples fall below legal limits. Modern wheat, bred to shed its husk at harvest, offers little protection. Ancient grains like einkorn and emmer, by contrast, keep each kernel sealed inside a tough hull, a natural barrier that can block some of what is sprayed on the field from reaching the grain inside. After threshing, that husk is stripped away, taking much of the surface residue with it. The difference is subtle, but it adds a second layer of concern. Not just what is bred into the wheat, but what is left on it. In the hills of Sardinia, bread is not a forbidden food. It is a daily ritual. Centenarians gather around wooden tables, breaking open loaves that trace their lineage to grains older than the Roman Empire. Researchers who map the world's blue zones, regions where people frequently live past 100, found something unexpected. These communities eat bread and pasta every day. But their flour comes from ancient grains leavened slowly with wild sourdough cultures, not the fast-rising refined white flour found on supermarket shelves. In Sardinia and on the Greek island of Icaria, families still use heirloom wheats, sometimes including einkorn and emmer, grown in small plots and milled in village bakeries. Artisan bakers and small farms across Italy and Turkey are reviving einkorn, driven by both tradition and a new wave of health seekers. Many people who struggle with modern bread report they can eat these old-world loaves without discomfort. The revival is small but growing, a quiet return to a grain that once fed empires. Today, most bread on our shelves is genetically engineered for profit, not health. As autoimmune diseases and food allergies surge, the grain we choose shapes our future. Returning to ancient wheat isn't nostalgia. It's a conscious act of self-preservation. The real revolution starts with what we plant next.